Okay, so our next talk will be given by George Ambrosiadis from the University of Toronto. By the way, he is graduating this year. This is a paper with his advisors, Angela Dempke-Brown and Ashvin Girl, and the title is Opportunistic Storage Maintenance.
Thanks, Andrew. Hello, everyone. So what I will be describing to you today is what we call opportunistic storage maintenance. But I think it's appropriate to start by telling you what we define as storage maintenance. So you've undoubtedly come across storage maintenance before. These are tasks that run periodically in the background on your laptop, on your desktop, on your server. These can be tasks like backups or virus scanners that are performed once a week or more or less often than that. The common thing between these tasks is that they tend to access large amounts of data. They can process all files in a file system, or they can scan every block on a block device. And they can operate on both the user level and the kernel level. So you can have user-level backup applications, or you can have a file system garbage collector operating within the kernel where it has access to data structures that it needs. So why are we bothering with storage maintenance today? So the thing with storage maintenance is that it offers essential guarantees for storage systems. And these guarantees can range between reliability guarantees that are given by tasks like scrubbing, which check the correctness of data on your device, to availability guarantees, which is given by backup, performance guarantees with defragmentation, security guarantees with antivirus checkers, and so on. And maintenance provides insurance today against disasters, and without it, there can be severe consequences. There are many examples almost daily that show us what these consequences can be. For instance, just earlier this summer, the US Bureau of Immigration was unable to process visas for 2 entire weeks. The reason for this is, well, they disabled backups because they interfered with visa processing during high tourist season. Of course, this is the perfect time for hardware failure to occur, and they had no up-to-date data backups. Now, I was actually one of the people that were affected by this, and my internship was delayed due to that. But even in the middle of that mess, I can't really blame them, because it's really hard to decide when to run maintenance. And the problem with maintenance today is that maintenance tasks can significantly impact foreground applications because maintenance tasks run alongside the workload and they tend to access a lot of data. As a result of that, they interfere with the workload, they increase seek times to your device, and they can pollute caches. The solution we have for this today is that we tend to schedule these tasks around the workload. We typically do that in 2 ways. We either perform maintenance during scheduled downtime periods, where the system goes offline and you do maintenance. Another approach that is gaining more traction lately is to perform this maintenance work while the device is idle. So basically what we're doing is trickling this work at low priority. But the thing that both of these approaches assume is that there's going to be sufficient idle time to perform all your maintenance work without impacting the workload. And well, today there's just too little idle time, because idle time is expensive. First of all, no one wants extended downtime periods for maintenance. I think that goes without saying. In fact, to get better storage efficiency, we've moved to the cloud, where higher consolidation ratios further reduce idle time. And while there's a shortage of idle time, there's really no shortage of maintenance work that needs to be done. So there are studies that show that enterprises perform full backups every 1 to 4 days. And as you may know, full backups take quite a bit of time. More specifically, one of the reasons is that storage device access times today increase slower than their capacities. For example, if you take a 6 terabyte hard drive, it takes about 10 hours to scan it from beginning to end. And as if that's not bad enough, we're not just dealing with one maintenance task. We're actually dealing with many tasks, as I showed you in a previous slide. And each one of these tasks basically adds the total maintenance I/O that we need to perform. So when you look at having too many tasks, well, these tasks tend to usually access the same data. For example, if you're backing up and defragging your file system, there's a lot of overlap between the I/O that these tasks need to perform. And you would expect that caching would help. It should be able to exploit data reuse between these tasks. But that's simply not the case, because cache data tends to get replaced before it's reused by all the tasks. This happens because each task accesses way more data than fits in your cache, and also these tasks tend to process data independently of one another. So let me tell you why processing things independently is a problem. So consider you have 2 tasks, task A and task B. They're deployed in your file system, and they both access all files. But task A processes all files in a breadth-first order. That's how it traverses the file system. So in the image that I show there, it will process file F1 before F2. And you have task B, which traverses the file system in depth-first order. So it's going to process file F1 before it processes file F2. And because of this different order of processing, these tasks may not get very good cache hit rates. But even if they were processing things in the same order, all it takes is scheduling them at different times to cause the same problem. So basically, if you have task B starting earlier than task A, it accesses some files. So by the time task A gets started and accesses the same files, the data is evicted from the cache, and you need to bring it back from storage again. So the result of this is that the maintenance I/O that you need to perform at the end of the day is proportional to the number of your tasks, even when these tasks are accessing the exact same data. And this is really the problem we're trying to solve. We're trying to reduce maintenance I/O for these tasks. The problem, the way we perceive it, is that these tasks are not accessing data in the most effective order. But at the same time, if you look at what they're doing, their correctness is not really tied to the order in which they're processing data. For example, if you're trying to back up a file system, you don't really care if file F1 is going to get backed up before or after file F2, as long as both of them get backed up at the end of the day. And so what we want to do is adapt the order in which tasks are accessing data based on what other tasks are accessing. Let me give you an example. So imagine you have a number of files in storage, and you have two tasks, a virus scanner that wants to scan file F3, and you have a backup process that wants to back up file F1, then F2, and then F3 in that order. So the backup process reads file F1 from storage, backs it up, then the virus scanner reads file F3, it scans it for viruses. That's the point where the backup process can realize that, well, the virus scanner has a copy of file F3 in memory, so I should just grab that. But I don't want to process it just yet, so maybe I should prioritize it and ask for a copy from the virus scanner. And it can do that, and then it can back it up, and then move on to do what it will anyway do, which is to bring file F2 from storage, back it up, and move on. Now, the problem here is that we need a way for tasks to determine what is accessed by other tasks. Specifically, we want our backup process to realize what the virus scanner is doing. And the answer is that we could look in the cache, because you would expect that recently accessed data will be there. And then what we could do is we can opportunistically process that cache data first. So going back to the example that I mentioned before, I'm adding just a cache layer now. So the backup process starts, it backs up file F1, reads it from storage. The virus scanner reads file F3 from storage, scans it for viruses. At this point, a copy of file F3 is actually in the cache, so all the backup process needs to do is look in the cache, realize there's a copy of a file there that it might need, prioritize that file, grab the data from the cache, back it up, and then move on to file F2. And so the problem here is that we need a way so that tasks can find out what is in the OS cache and whether they're interested in it. And what we do is we basically expose cache information. Now, operating systems today cache data at page granularity. So to make this more concrete, what we need to do is expose which pages are cached. And the way we do this is that we have a framework which tracks changes to the status of cache pages. These are changes like if a page is added or removed to the cache, if it's dirtied or flushed back to storage. Then tasks can register interest on specific events. They can say that they want to be informed if a page is added or removed. And they could be more specific. They can say, well, I only want to know about pages that belong to files within our /home directory or on a given block device. And finally, tasks can go to the framework, poll for events that they're interested in, and they will receive events that uniquely identify changed pages. And the way we do this is that we've structured our events so that they consist of a page identifier, which contains an inode number, and an offset of the page within the file, or the block device, whatever the inode is. And also some flags that describe what is the change that occurred to the page. Like, for example, it was added and modified. And so we've implemented this framework to expose this information. We call this framework Duet. There's an implementation for the Linux kernel. And it resides within the kernel. It is a module. And it hooks into the cache to get the needed information. So the hooks in the cache are very simple. They're just, whenever they see an addition of a page or removal of a page, what they will do is that they will relay the information of that event happening back to the framework, and the framework can collect all of this information. And then you can have tasks that are in the user level or in the kernel level, and then we expose a uniform API to all of these tasks that they can use to poll for events that they're interested in. So what I haven't specified so far is how do these tasks use our page events? So that's what I want to do next. So recall that basically the goal we have here is to use page events to enable tasks to achieve a more effective processing order, right? So events, on the one hand, the problem is that events describe changes to pages while tasks might operate at different granularities. So they might be processing items like files, if you're backing up files, or extents, blocks, segments, if you have a log-structured file system segment cleaner. But the thing that is common between all of these granularities is that they are multiples of a page. So we can use our page events to help tasks see what portion of an item is actually in the cache. So let me give you a concrete example. Imagine you have a file defragmentation task. It can use added or removed events to track cached file pages, or for the files it's interested anyway. And then what it can do is it can prioritize the processing of the files that have the most cached pages. And so it doesn't need to fetch these pages from storage, and so it doesn't have to perform that I/O. So this is what we call opportunistic processing. And to give you a more concrete example of how a task can be made opportunistic using Duet events, this is what basically, so the maintenance tasks that we have studied, and we've looked at a number of them, I'll show them in the next slide, follow a common structure in general. They consist of a main loop, like the one you see in the figure there, where in every iteration, an item, like for example a file, is selected and then it is processed. And so the way that there's usually a procedure that selects files in a certain way. So the task, it might be implementing something like a depth first order traversal of the file system. And every time a file is picked, it's handed off to another procedure which will defrag the file or back it up or whatever the task is doing. So what we do for all these tasks is pretty consistent. We place a block of code right before the choice of a file is made. And then what we do is that we try to see if there's anything in the cache that is of interest. The way that we do this is that we communicate with our framework through its API. So we fetch any events that might be of interest. And then we update the tasks, the way that the task sees the cache, basically all the information that it contains about what is in the cache. And it can update, for example, a priority queue that stores files based on how many pages they have in memory. Then you can go to that priority queue and dequeue the files with the most pages, or until it runs basically out of files with cached pages, and then you can fall back to processing files in standard order. There's a subtle problem here, which is that if we're deviating from the standard order that the task is doing things, we might end up processing things multiple times. So to avoid that, you could obviously do bookkeeping within the task. We would like to help developers with that. So as part of our API, we provide calls that allow them to check if a file has been processed before, and so they can avoid it. Now, we have used Duet with a number of tasks. Btrfs, which is a copy and write file system for Linux, already implements a number of maintenance tasks in its code. For example, a scrubber, backup, and defragmentation. And we've modified all of these tasks. So what the scrubber is doing is basically going through all the data blocks on the devices in the order of a block number, and it checks to see that the data that they contain match their checksum. So what we've changed here is that we don't scrub any recently read blocks, because every time you do a read operation, the checksum is checked to ensure that the application is not going to get corrupt data. We also modified the backup process of Btrfs. The way it works is a little bit special in the sense that it takes a read-only snapshot of the file system, and then it starts copying the blocks to backup storage. So in this case, what we're doing is normally it's going through files by inode number. But what we're doing is if we see any in-memory blocks that belong to that snapshot, we just send it off first. The defragmentation task works much like the example I gave before. So normally it goes through all the files in the file system by inode number. What we've changed here is prioritize the files with the most cached blocks. So we also modified the garbage collection for F2FS, which is a log-structured file system for Linux. It's targeted for Flash devices. As a typical garbage collector, it relies on a cost function that picks a victim segment to clean. And what we've done is adjust this cost function to account for any blocks that are cached. Finally, we've also changed the user-level app, because all the previous ones are operating within the kernel. The user level app we picked was rsync. So for those of you that are not familiar with how rsync works, you give it a source directory and destination directory, and it synchronizes the contents of the destination directory to match those of the source directory. The way it does that is basically traversing, a simplified way of how it does that, is go through all the files on the source directory in depth first order and send them over to the other side. So what we've changed here is prioritize files with the most cached pages to be sent out to the destination first. Now, what I want you to notice for all of these tasks is that the number of lines that we had to change were usually a couple hundred lines. And most importantly, they followed the structure that I showed you before. There was a loop, and we always placed a block of code before the task picked a file to look into what's available in the cache. So in terms of how we carried out our evaluation, the goal that we had was to evaluate our framework's ability to reduce the amount of maintenance I/O that needs to be performed. And the way we set up our experiments to see that was, first of all, we ran one or more maintenance tasks alongside some benchmark workload. In our case, we picked file bench workloads. And we measured the amount of maintenance I/O that was saved when the experiment was run over a fixed amount of time. In our case, that was 30 minutes. And one thing I should point out is that the way we've scheduled maintenance I/O is so that it is only performed if the device is idle. So that way, we do not interfere with the workload, increasing latency of those I/O operations. Now, we've varied a number of parameters of the workload, 2 key parameters specifically. One of them is data overlap, which is the fraction of maintenance task data that is also accessed by the workload. The reason this is important is because if there's a high overlap between the workload and the maintenance task, the workload will bring data in the cache, which the maintenance task can then piggyback on. It can use it. Another parameter we varied was the device utilization. This is the amount of time that the device is busy, but when it's running the workload alone. So that doesn't count the maintenance task. What this means is that as the workload is utilizing more of the device, there's less idle time, so we have less time to actually do maintenance I/O. And the way I'll be presenting our results is I'll be using 2 sort of ways to visualize it. The first one is going to be a graph that looks like this. On the x-axis, you have the device utilization by the workload, which means that on the left-hand side of this axis, you'll have a 0% utilized device is a device that's idle, and then we're running a maintenance task on it. On the right-hand side, you have a 100% utilized device by the workload, which means there's no idle time to perform maintenance I/O. And then on the y-axis, what you have, we measure the maintenance I/O that was saved by using Duet, and generally it is higher is better here. So basically what this means is that 100% I/O saved means that the maintenance task had to perform no I/O because it was piggybacking on other things that were happening on the system. Another tool I'll be using to visualize our results is a table that looks like this. What it shows you is the maximum device utilization as a percentage by the workload that we can tolerate while still completing all of our maintenance within 30 minutes. And here, higher is better because if we can tolerate a highly utilized device, that means that we can complete all our maintenance I/O in less idle time. So the first setup we tried is running just one task and the workload. The results I'll be showing you are just for Btrfs backup. So the line that you see there refers to running backup alongside a workload that has a 25% overlap with it. So it's accessing 25% of the data we want to back up. So initially, when the device is idle, there's no workload, there's no chance for you to save any I/O. But as you increase the device utilization, there's more chances for you to save I/O until you reach a point where the workload is accessing all the data that is common between that and the task. And then you save 25% of your I/O, and that's when your savings plateau. And then as we vary this overlap of the workload with the task, you can get more benefit. And what I want you to take away from this is that basically with Duet, you can exploit all opportunities to reduce I/O depending on the overlap you're going to have with the workload and how utilized the device is, because you want the workload to access things first generally, if you want to piggyback on that. But an important data point, for example, is this one where you have 100% overlap between the maintenance task and the backup task, and the device is 100% utilized by the workload. But that's okay because the backup task does not need to do any I/O. It basically piggybacks on all the workload requests. And you might be wondering if this is a realistic scenario. Well, consider that you're doing an incremental backup, in which case what you want to back up is everything that the workload accessed and changed. So in terms of how that benefits us in terms of time, we can tolerate more utilized devices. Now, when it comes to the baseline, it doesn't really care how much overlap there is because it's not doing anything different for different workloads. So if what I show you there is 40% is the maximum device utilization we can tolerate. Any device that's more than 40% utilized by the workload, and we can complete our maintenance within our experiment at least. But with Duet, we can tolerate more device utilization because we need less idle time, because we need to do less maintenance I/O. And the data point that I pointed out before is that if you have 100% overlap, well, you don't need to do any I/O. So if the device is fully utilized by the workload, you can still complete your maintenance. Another thing we tried is running multiple tasks together. Specifically, we ran scrubbing, backup, and defrag at the same time. So generally, this is a pretty crazy thing to do because if you were to do this, you wouldn't expect anything else to be done. But when we tried to do this in our system, we only had to actually perform 50% of the I/O on a completely auto device, just having these three tasks run together. And that was because they actually piggybacked on one another. So whenever the backup task brings something in memory, the scrubbing task can actually scrub it, and the defrag task can defrag it. And what we did is on top of that, we threw a workload. And so we can get more savings if the workload is accessing things that we're interested in at the same time. And it can get to a point where we can save up to 80% of our I/O because we're piggybacking on the workload as well as other tasks. The reason, by the way, that this is not 100% is because for the defragmentation task, we absolutely, at the end of the day, need to write back the defragmented blocks to storage. And there's no way to save that. So in terms of whether we can complete the work in 30 minutes, well, for our baseline, we can't. Running scrubbing and defrag and backup cannot complete in 30 minutes. But with Duet, it can, and not only that, you can also run a workload that has some overlap with it. And you can tolerate the device being utilized by the workload at the same time. And you can tolerate utilization of between 30% and 50% depending on this overlap. So one last thing I want to talk about is what is the overhead of running Duet? We've measured it to have a low CPU overhead. The way we did this is that we ran FileBench at full device utilization, so it generates a high rate of page events. And we had a task register for all page cache changes, so we wanted to know everything that was going on in the cache. And then we had it also aggressively fetch events every 10 milliseconds. The way I say that this is aggressively is because all the tasks that we monitor tend to fetch events every 20 milliseconds or less frequently than that. And even in this setup, the CPU overhead we measured was less than 1.5%. Also, the memory footprint is pretty low. For Duet, right now in the current implementation at least, all we need is 64 bytes of metadata per page. And by the way, that only applies to pages that have pending events. So if you're fetching more frequently, you're not going to have to keep all these events around. Like if you have 4K pages, that's a 1.5% overhead, by the way. All right, and with that, I'm going to, in conclusion, the problem that we're trying to solve is that current maintenance tasks are work independently of one another. And so our approach to this is to enable collaboration between these tasks by allowing them to piggyback on one another, much like the carpool lane in a highway. And the steps we take is that first, we expose changes in the page cache as events. And then we have tasks poll for these events to detect any cache data that might be of interest to them. And then they can use these events to reduce the I/O that they need to perform by reordering work to process cache data first. So I've put the source code for Duet on GitHub, and I would love for you to try it and see if it works for your scenarios or whatever scenarios you come up with, and let me know. With that, I'm going to open the floor to questions. Thank you.
Jay Lorch, Microsoft Research. Good work. I appreciated hearing about it. I appreciate also that you limit Duet's access to only being able to ask about files that you have permission to access, but I'm still worried about it amplifying side channel attacks, where one process can see the internal behavior of another, in your case, by observing accesses to shared libraries.
That is a very valid concern. So we tried to address in the paper, so our current implementation doesn't address it, but the way that we can do this is basically, before returning an event, we can check to see if whoever is the user, the person that's actually requesting the event, has access should have access to that specific inode or that specific page within that inode. Does that answer your question?
Oh, well, but there are still pages that I might have permission to access, but I don't want to have such fine-grained permission to see the
So
time.
we don't actually do anything about that right now. Generally, it will be the administrator or someone with a higher power that's going to run these tasks to begin with. Which is
Yeah, I was wondering, maybe you want to restrict the permissions even more, that you shouldn't be able to access Duet unless you have administrator permission.
Yes, that would be a great idea, actually. Thank you.
And Jeff Kenning, Harvey Mudd College. I'm a little bit curious about unintended effects. So in particular, in your backup stream, you're changing the order of the backup stream. A lot of backup systems use deduplication, and the deduplication systems depend upon getting the same order every day. And so it seems to me that you may be harming the deduplication unintentionally while you're speeding this up, and that may actually harm the performance of your backup of the entire system.
That's interesting. So my understanding of deduplication is that for every block of a file, you would check the fingerprints. So it would be, so the order in which you were doing this would not be dependent on, you know.
No, actually, deduplication systems depend heavily on caching and locality for speed.
Okay.
Kurt Collefson, VMware. Interesting work. It seems to me that this is highly dependent on timing. That, you know, if things are temporally distributed in time, you may have aged out these blocks. Have you considered something like a pub sub model where, you know, if you wanted to encourage this collaborative page sharing, if you will, that, you know, you'd have like a scanning daemon that these various maintenance tasks could subscribe to, so that, you know, you don't have to be so careful about when you start these, starting at the same time and things like that.
This is a great idea. We didn't try it here. Our assumption would be basically that the administrator would be in charge of deciding when to run these tasks, and it would run them all together potentially. The other thing is that, you know, if we're trickling work over time, maybe, you know, running these tasks is going to happen over a longer period. But I mean, what you're pointing out is a very good point. Like, you could have, for example, a task, which is a dummy task, that accesses all blocks on a device in some optimal order, whatever is the optimal for that device, and have the task actually subscribe to that. You can do this right now with Duet as it is.
Hi, Fred Douglas, EMC. So I was wondering, isn't opportunistic maintenance kind of a low-hanging fruit? So basically, you're tackling things like backup, but you have all sorts of other applications like make and MapReduce and other things that are accessing lots of things possibly in any order, and you could use the same thing for application-level things.
Yeah. So this is something that we're looking at right now, actually. It's one of the extensions that we're looking at for this model, yes.